Hello, and welcome to video lecture number 9, which covers section 1.5, day 2, Analyzing Graphs of Functions. In order to satisfy today's objective, you need to be able to analyze a graph by approximating its relative extrema, calculating its average rate of change, and identifying whether it's an even or an odd function. Part 1 of the notes describes relative extrema, and these are the points at which either the graph will go from decreasing to increasing, in which case we call them relative minima, or where the graph goes from increasing to decreasing, in which we call these relative maxima. When finding these points, you want to pay attention to where the graph is changing its direction, so either at the top of the hill or the bottom of the hill, so to speak, and you're going to have to find the x-coordinates of these points prior to describing whether it's increasing, decreasing, or a constant interval. Before, you were given those points and you were able just to write interval notation. Now you're going to have to find them first and then describe it. The relative minima and relative maxima values are so important to the study of functions because whether this is a graph depicting the price of a stock over time or the number of users on a website over time, these points denote change, and anytime change is happening, we want to focus our attention around that change, try to understand it, and then see if we can make predictions going forward based on those patterns. So in example 1, we're given a series of functions, and just like before, we're asked to determine the x-intervals on which these graphs are increasing, decreasing, and or constant. However, we do not have the graphs in front of us. We actually have to make the graphs on our own and then determine at which points is the graph changing direction so we can do that. So I will try example 1a with you first. So if you have your TI graphing calculator in front of you, to do this, you first want to graph it, and then you're going to want to find that maximum point or minimum point, depending on where you're at, using the second button, then hitting the trace button and selecting either maximum or minimum. I will show you now how to do this on a separate graphing calculator from the internet. So once again, I've pulled up the free online graphing calculator from Desmos.com, and once you enter the function, you'll have to press that second trace and then select maximum in this case. Now with this graphing calculator, it automatically gives me the maximum value, and that is -4, 5.657. But remember, we are concerned with only the x intervals for which the graph is increasing. So I'll shade the increasing part, and then we're going to write that the graph increases over the interval -6 with a bracket because we use -6 to -4. Now the remainder of the graph, as I read left to right, is a decreasing segment, and that decreases the entire way to positive infinity. So decreasing, we would write -4, positive infinity. And remember, we are using x values to describe our increasing and decreasing intervals. Please make sure that you copy a sketch of this graph on your example 1 in your notes to have a better understanding of what we just completed. So I went ahead and moved on to example 1c, and I've graphed the function and already have noted the relative max at -2, 3, and the relative min at 0, -1. Now we will try to determine the increasing and decreasing intervals. So I will shade in red as I read left to right the increasing segment of the graph, which stops increasing at x -2, and it then continues to increase from 0 on to infinity. So again, these are the increasing segments of the graph, and we will then write our answer in interval notation. So increasing, beginning on the far left with -infinity for x, and then we get all the way to this -2. But then again, we start increasing once again when x is 0, so we'll union with 0 to infinity. Now we will try the decreasing. This graph is decreasing as I read left to right what I see shaded in blue. So notice that the x intervals for which this graph is decreasing go from -2 to 0. So I will write that in interval notation. Once again, these are x values, not y values in my answer. So please take a moment to try example 1b on your own if you haven't, and please copy your graphs from your calculators onto your papers and note the relative max and relative min points as part of your answer. Part 2 of this video lecture discusses average rate of change. So take a look at the graph below, and I want you to assume that this is the graph displaying the price of a stock over a certain time frame. Let's suppose that x1 represents year 1 and x2 represents year 2. And if you look at the growth of this stock, notice its speed of growth is not exactly the same throughout year 1 to year 2. Notice it speeds up and then all of a sudden starts to slow down and then actually decrease a little bit. Now, if we were to then assume that the growth of this stock stayed the same throughout the entire year, then what we would be finding was its average rate of change. So how do you calculate the average rate of change? Conveniently, this line that passes through the graph is known as a secant line, and it's also a straight line. Therefore, if we have 2 points, the only thing we need to do is find the slope. So the average rate of change is also referred to as the slope, and remember that the slope can be calculated using the formula y2 minus y1 over x2 minus x1. And recall, for the past few days, we've been learning that y values can also be written as f of x to denote functions. So instead of y2 minus y1, notice we can also write f of x2 minus f of x1, and that means exactly the same thing. Finally, all of those things above are equivalent to writing m for slope and then subscript SEC, which stands for secant line. So msec is a way to also abbreviate the average rate of change. Example 2 asks us to find the average rates of change given the function f of x equals x squared plus 2x. So using that function and the given x values, the first thing I want to do is graph the function. Once I get a graph on my graphing calculator and I can transfer it to the paper, I then want to observe the 2 given x values, -3 and -2. I need to find those corresponding y values so then I can run the slope formula. So either by looking at the table of values from the graphing calculator or plugging them individually into the function as you see below, I determine that the y value for x is -3 is +3, and the y value when x is -2 is 0. Now we have enough information to find the average rate of change between these points. Now we will calculate the slope of the secant line that connects the 2 points as if they were on a straight line. So to do that, we will run the formula y2 minus y1 over x2 minus x1. So I will plug in the y values that we just found along with the x values that we were given, and we will simplify. So the slope of the secant line is -3, and we will denote that with msec as an abbreviation. And so as we read the graph left to right, what that means is, on average, the graph decreased -3 units throughout x -3 to x -2. Using example 2a as a basis, please try example 2b on your own and have it ready to check for tomorrow. The final part of today's video lecture describes even and odd functions, and you may be surprised to know you've already learned about this, we just didn't call it even and odd functions. In section 1.2, we found symmetries of a graph, and those were y-axis, x-axis, and origin, and now we are going to focus specifically on 2 of those. So when we say a graph is even, we mean it has symmetry with respect to the y-axis. So now y-axis symmetry should be known to you as an even graph, and odd refers to a graph that has origin symmetry. Let's start by looking at example graphs for each even and odd functions. Let's start with the even function, and if you look at the graph on the left of the parabola, notice we call this even because it has y-axis symmetry. So those things are interchangeable and you can use them going forward. Now, you'll notice that there's a piece of information that reads in the definition f of negative x equals f of x. Well, I've tried to translate that for you because earlier when we talked about y-axis symmetry, remember we said that when you replace x with negative x in the equation, you should end up simplifying and get right back to where you started with the same original function. If that happens, that is another indication that the graph is even. The graph on the right displays origin symmetry, and therefore we can call it an odd function. So when you think origin symmetry, think odd. Now, the definition that is in symbols off to the right reads f of negative x equals negative f of x, and what that can be interpreted to mean is when you replace x with negative x, you actually get an opposite equation as the original, and by opposite, I mean the signs of the equation you end up with will be exactly the opposite as the signs in the original. So example 3 gives us various functions and asks us to determine whether these functions are even, odd, or neither, and we need to verify our work both graphically and algebraically. So I'm going to try example 3C with you, and I'd like you to try A and B on your own. Now I went ahead and graphed, or at least showed you the sketch of my graph for 3C, and I can suspect already by looking at the graph, since it shows up in the opposite quadrants, if you will, these corner quadrants, I probably have an idea that it's most likely an odd function. Remember, it's definitely not even because I cannot fold it across the y-axis and have the graph match up. So I suspect that it's odd, so I'm going to try the test for an odd function with the algebra. So if this function is indeed odd, I should be able to verify that by plugging in negative x, I actually get the opposite of the original function we started with. So I went ahead and started by plugging in negative x everywhere I saw an x in the function given. Now what I will try to do is simplify. When you simplify negative x cubed, you end up getting negative x cubed. So that negative can be brought to the front, and we have negative 2x cubed, and 3 times negative x is negative 3x. Notice the signs of both of these terms. They are both negative, whereas in the original they were both positive. So this indeed shows that this function is the opposite of the original, and we have shown that it is an odd function. Use example 3C as a guide to help you complete 3A and 3B on your own. Have them ready to check for tomorrow. This concludes video lecture number 9. Please take a moment to look back over the notes in the video lecture and determine at least one question that you have and write it down and have it ready to go for tomorrow. Thanks again for watching and good luck.